Wow, those are a lot of very nice things to say. Um, Thank you, Megan. Um, well, I guess that I don't need to repeat my name, but thank you for being here. And my project is centers around integrating data science for disease classification, prediction, and expanding access in limited internet settings that don't sorry, and in limited internet, like in limited settings, and oh my God, in settings that have limited internet access, um, that are trying to teach data science. Oh, trying to switch the slide. Okay, there we go. So uh, two of my projects revolve around vector-borne diseases, specifically emerging vector-borne diseases. But we're going to start a little bit like earlier than that, or maybe a lot earlier than that, and I'm going to and we're I'm just going to tell like a story on how vector-borne diseases have been occasionally like a force behind the rise and fall of empires. Um, so I decided to start the story in the Caribbean in 1791. And at that time, Haiti is one of the most profitable colonies that France has. They provided at some point like half of the global sugar and coffee production. Um, and after the French Revolution, some of the French colonies also started revolting. Napoleon Bonaparte was determined to keep a strong presence in the Caribbean, and then he sent like around like 60,000 like soldiers to suppress this rebellion. And by 1804, between 80 to 85% of the soldiers had died of what they called yellow jack. And yellow jack is better known today as yellow fever, and it's a disease transmitted by a mosquito that is more commonly found in South America and Africa. And the French soldiers were not familiar with it. It is also believed that Napoleon Bonaparte was planning to use Haiti as a springboard to invade Mississippi through New Orleans. And with most of like the army like dead, it was a failed expedition, and also like they also failed in the wanted like NA or North American like expansion. So we talked a little bit about vector-borne diseases, in which in this case it was yellow fever. So they commonly have like three main components, and we have the pathogen, which can be a parasite, it can be a virus, it can be a bacteria. Do you see my mouse? Oh, yeah, you do see my mouse. And then you also have a vector or an organism that can transmit or carry these pathogens, which are often arthropods. And then you can also have a host or a reservoir, but in this case, we're going to be focusing on the host, in which in our case, it's going to be people that get infected and that get sick. So now I want to introduce what's an emerging vector-borne disease, and so the emerging part of vector-borne diseases is the only difference is in the point of time and space in which it's occurring, and the disease is essentially emerging or new in the sense that it has never been there before, or it happened a while ago and it was once a major health problem, but it is not, it stopped being a major health problem and then it started being a major health problem again. So I made up the Never Sick Republic here. And so this republic is already populated by people. And then we have that vectors uh, with potentially like pathogens already inside there are like arrive there. And then the Never Sick Republic becomes like the Sick Republic because the people are already there. And then these vectors then they when they feed off of people, then they get to like transmit like those pathogens as part of the life cycle. Um, and okay, so what? Like who should care? Well, it's predicted that this is going to be an ongoing public health challenge that is going to keep persisting. And who should care gets to be answered with every scientist's like favorite answer of all time, which is it depends. Um, are we asking who should care today, or are we asking who should care tomorrow? Well, currently or today, between like the biggest burden of vector-borne diseases is carried by the subtropical and tropical like countries, and at a global scale, around like 70%, like vector-borne diseases composed of like 70% of all infectious diseases, which are diseases that can be communicated. To give a specific example, dengue, for example, like dengue, we have like 4 billion people. And of those 4 billion people, almost half of them, almost like 4 billion people are at risk of contracting dengue in over like 132 countries. And for example, like malaria, there are around like almost like 250 million cases globally that result in like around 600,000 like deaths per year, and of which unfortunately most are children under 5 years old. So those are the people that are caring today, but what about tomorrow? It is it is documented that the US is going to it is documented that the US is becoming warmer, and it is also becoming wetter. This that I'm showing here, these are not predictions. These are comparisons to the previous century. So we can see that that like through time in this century, that the US is becoming warmer, and it is also becoming wetter compared to like the previous century. And again, these are not predictions. These are just comparisons. And what happens is that vector-borne diseases, they are susceptible to changes in temperature and in humidity and precipitation. So they usually prefer humid environments that are not freezing. And some of them are limited more to warm environments, and some of them can be in the more temperate areas. But we can see, for example, this is mapping Lyme disease. You can see that in 1996, most of the Lyme disease cases were like here on the coast, and then in 2018, it has been spreading like to other areas that maybe they had like sporadic cases, but like there's a lot more cases in other areas where there were not that many before. And then to give another example, dengue in the US, in the contiguous US, so not including Puerto Rico or any of the islands, by 2014, there were almost like no dengue cases. And by 2023 or last year, there has been around like 200 cases that were locally acquired, meaning that this person did not travel anywhere that had dengue, contracted it. They were in their space, they were in the country, and they became infected locally. Um, and one of the main ideas behind some of my behind like two of my projects is that the next zoonotic outbreak might be etiologically novel, but most likely will be similar to previous counterparts. And so we just mentioned like the important bit being like they will be similar to previous counterparts. And So then vector-borne diseases, they have an added layer of complexity in the sense that they're not
parties. Yeah.
they're not communicated by direct contact in most cases. And they have like this vector, this arthropod, this tick or this mosquito that acts like as the carrier that transmits it to people. And because vector-borne diseases that are from different families, for example, that are the pathogens are not necessarily related, sometimes like get carried by the same mosquitoes, and they are regulated by very similar environmental and climatic like factors and biological like factors of like species interactions or even population density. So what I'm trying to say here is that even if some diseases are unrelated, they're not very similar because they share a common like vector, then they can still like certain certain variables can still like affect them like in similar ways. And so we can build on this, and we can also say that the next emerging vector-borne disease outbreak will also most likely be similar to the previous counterparts because diseases don't really happen in a vacuum, right? So these are diseases that it is most likely that they have been experienced in some other part of the world, or that even in the same country that there has been something similar to it, even if they are experiencing like this new outbreak. And how can we find like these similar like counterparts? Well, we usually, to find similar counterparts, we usually classify, right? So classification allows for us to compare within and across groups and to identify trends, similarities, and differences. And it is oftentimes guided by purpose. And what I mean with this is that let's assume that we have 100 diseases and that you're interested in exterminating vectors. You want to kill a lot of mosquitoes because currently you're having an outbreak. Then these 100 vector-borne diseases, you might separate them, and you might say like, okay, the ones that I'm interested in are the mosquito-related ones, and then studying them as a group might help you, for example, apply a pesticide at an optimal time of the day in which you might be able to like kill like more vectors. Doctors, another example, you have those same 100 diseases, and maybe doctors or physicians, they end up like breaking those 100 diseases into different subgroups that can be by the symptoms that they cause. So then that's what I mean by a guided purpose. But then a more methodological way of doing it is via clustering. And clustering essentially allows us to create groups or clusters. I'm going to be using that sometimes like interchangeably, that are based on patterns in the provided data. So you don't necessarily like label and say like, this is my intention, or this is what I want, because I'm using it for this. You provided data, and then the algorithm like determines based on the data that you provided which diseases are more similar to each other and assigns them to a cluster. And then if they're in a cluster, well, that's obviously saying that they're also in the cluster has a high in the cluster has a high cohesion. Then we can say then that they're most likely to be dissimilar to like the diseases in some other clusters. And for this project, we end up using PAM. And the key advantage of PAM is that allows us to select media. I'm not going to repeat it. They essentially like the center or like they allow you to have like as a center of the cluster an actual disease. instead of an average like centroid, which allows for a little bit more of interpretability. So then this leads us, so we build on this, and this leads us to comparing different approaches of clustering. So we're saying we have different ways of classifying these diseases as we saw earlier. And we want to cluster vector-borne diseases to identify distinct groups of vector-borne diseases. So then we are comparing different ways in which people like group diseases normally, and we're comparing them to like some like clustering based on data that we fed to the algorithm, and we want to find which share the most characteristics based on these. And we compare four main groups, and we compare four main groups of classifying diseases or clustering. The first one being pathogen biological clustering, family clustering. The second one being non-taxonomic feature clustering. Then the third one being a combination of, so we include information on the pathogen biological family, and we also include information on the non-taxonomic features. We merge them together, and we make new groups, and we make a new way of clustering in different groups. And then we also include the ICD-11 classification system. We're going to go over these a little bit more in the next slide, but just to make it very clear, the red ones are the ones that we created, and the black ones, pathogen biological family, and the ICD ones are already existing ones that we're going to be comparing. So then to do this, we first collected data, and we collected information on biological like family classifications from like the CDC, and the non-taxonomic features that we're talking about. We got them from Gideon, which is a global infectious disease of epidemiological network, and then the international classification of diseases. So the international classification of diseases is like a handbook that physicians and other like health related jobs like use to talk about like mortality, for example. And Gideon is just this it's this big database that collects information on that. It puts together information of multiple like open source multiple open source like information provided by the CDC, WHO, or even like open source like papers. Okay, so as we just mentioned, so biological family, we did not edit, so we're going to be using that in our comparison. And so like then the ICD-11 classification already exists. So then from what we got from Gideon, the non-taxonomic features, we used like PAM clustering on them, and then we created a non-taxonomic feature clusters, and then we also combined them then with biological family, and then we created this other one. So, and then we created biological family with non-taxonomic features clusters. And then what we ended up comparing were all the ones that are in blue. So the ones that we did nothing to, and then the ones that are the non-taxonomic ones, and then the non-taxonomic ones in which we added like biological family. And just to be a little bit more explicit, some of the non-taxonomic features are, for example, like fever range and vector genus, for example, or like the genus of the disease transmitter, a list of animals that can become infected, alternative routes of transmission, for example, like some vector-borne diseases have also been recorded to be sexually transmitted, pathogen type, and countries in which these diseases occur. Okay, so these are the results. So when we compared family clustering to family clustering plus non-taxonomic like clustering, we found that most of the pathogen family groups stuck together, and they went to the same cluster, with the exception of three families here. And our first cluster, just to give them some names, are essentially like tick-borne rickettsial and spotted fevers. The second one being tick-borne hemorrhagic fevers and encephalitis. The third one being more like on bacterial infections. The fourth one being more on mosquito-borne viral encephalitis. The fifth one is just composed of one group. The sixth one is more on mosquito-borne like fevers. The seventh one is parasitic infections, and the eighth one is more on protozoan infections. And we found when we compared, so that was comparing family, biological, comparing pathogen family compared to the one that we just did to like itself plus like non-taxonomic, and this one is just family clustering plus like non-taxonomic features. And we found overwhelmingly almost like the same thing. There were like three groups in which there's only a difference of one with the other one. That overwhelmingly the families went together to like the same clusters. This was not the case when we compared family clustering with the ICD-11 or like with the ICD-11. There was no overwhelmingly evident like pattern. And this was also the case when we compare it to like non-taxonomic clustering. And again, when we, so, and when we included family clustering to the non-taxonomics, there was also like no specific trend. So like the key takeaway from this is that different approaches to clustering, such as like the different methods of classifying that we just mentioned, can lead to different perspectives, right? And that biological family can be useful because it provides more of an integrative like perspective. And that in some cases, if you're trying to cluster and you're indiscriminately, then biological family might be enough. In other cases, if you have a very strong idea of why of the information that you want to provide to make the cluster, then there are definitely like this can also be done, and we found that some of our features did very, very well, like when we use them individually or like in subgroups to like cluster. So so then we did build a little bit on this, and so what? Like what can we do with that? Well, the next question is can we use disease data proxies, or can we use diseases that are similar in like the same clusters, for example, to improve prediction of an emerging vector-borne disease? So a disease that is new in an area, can we use a better known disease? Can we use its information to improve the predictions of this new disease that we have little data on? And why would we want to do this? And why would we want to do this, right? So essentially being able to predict like accurately would allow us to allocate resources better. So we can go with, so we have, for example, this person that became sick, and it's known that like they were exposed to like some vector, or they can recall it, and then like that's reported, for example, to the CDC or the NIH, and then more like the CDC, and then like and researchers there like can some researchers there could for example say like, oh well, like this disease seems very similar to this other one, and then even if we don't have a lot of information of this new one, we can still use some of that information with the purpose of informing the people that can actually distribute the money or the resources to give targeted surveillance and to promote like more promote more research or to starting to develop vaccination efforts and to also give them these in a targeted way. So if you predict like more accurately of where diseases are going to be occurring in your country, then you can start sending resources to those areas to help like mitigate like the spread. And a little bit more specifically, um, uh, a little bit more specifically on my project, well, wanting to inform emerging vector-borne diseases with a proxy disease, and to improve the predictions of disease dynamics of less known diseases. But we would be using a case study in Puerto Rico of dengue dengue information on the 2010 to improve the predictions of the newly emerging Zika in 2015 and 2016 in Puerto Rico. And why do we think that we can do this? This is from a proposal of Miguel. Anyway, so here, for example, we have chikungunya and we have Zika. These two pathogens they're not related, right? Like one is chikungunya is an alpha virus and Zika is a flavivirus, and still, but they get transmitted by the same mosquito, by Aedes aegypti, and we can see that they follow very similar like spatial patterns, right? So we have the very populated like San Juan and Ponce, for example, and we can see that these spaces in both of the diseases have a not higher number of confirmed cases. And because of what we mentioned earlier, that pathogens are sensitive to changes in climate, and that there's also like biotic like factors that influence them, such as like population density, because you have a vector you have a vector that already has like the pathogen inside of it, and then it gets to like it feeds off of a person, and then that person gets bit by like a mosquito, and then that mosquito acquires like the pathogen, and then if there's 10 people in that household, it is most likely, and you have also mosquitoes like inside of the house, then it is most likely that most of those will become infected if they live in very close proximity. And this is something that is not necessarily just restricted to vector-borne diseases, right? When COVID came out, they found that it shared almost like an 80% of its sequence identity with SARS, and they used some of the SARS and MERS like models as references for the COVID for COVID and to predict like COVID, especially like in the early days. Sorry. Okay, so what would we need to be able to like create these models? So we would need the census data from 2010 in Puerto Rico, which would be tied to the dengue number of like cases from 2010, and also like the temperature for 2010. And then we would also need the 2016 data, so the population estimates, because there wasn't a census in 2010, but the census does provide like estimates. And then for 2016, like the numbers of Zika cases, and also like the temperature. But I just wanted to like note that the Zika cases are on a weekly scale, but the dengue cases are in a cumulative, like just by the end of the year. So we have one data, one point of data for each one of the municipalities of the total number of cases of that year versus like in SICA, we had like different weeks as it was like progressing. And why do we think that we can use like why do we use like dengue 2010 dengue data to inform 2015 SICA predictions? Well, this whole graph up until this point, up until here, this is all like dengue, like number of dengue cases that were reported by different like reporting organizations. So then we have like the total count of cases. We have like the year in which they happened, and all of these are dengue. The only one that is SICA is this one. So and we picked 2010, which is this one, because it predates both Zika and chikungunya, which occurred in like in 2015 and between 2014 and 2015. So then when we're using dengue to inform our Zika models, then we know that those are dengue cases and not Zika or chikungunya cases that were reported incorrectly. And how we did this was we first like collected data as I just mentioned on the 2010 like dengue 2010 dengue temperature and population in population like and population. And then for the 2015 and 2016, like Zika cases, temperature, and population. And the cases were per municipality. And then we use a Bayesian like generalized linear mixed model. Because essentially it allows us to include information it allows us to include information, for example, from like priors. And it helps us like in that way, like deal with uncertainty. So this needs to be like, okay, so we modeled dengue and then we obtained posterior distributions from that dengue model, model. And then we did the same model, but for Zika, and then we got predictions from there. And then we used the posterior, like, then we informed the priors of the Zika model with the posterior distribution of the dengue model. And then we also ended up getting predictions from there. And then we ended up comparing a model that's informed by dengue and a model that is not informed by dengue. And what we expected was that the models that were informed by dengue the Zika models that were informed by dengue would do better in the early weeks. So the early weeks being like the weeks with the least amount of data. And then this would be an intermediate week in terms of data. And this would be like a late week in which there's already like a lot of like Zika cases. And so what we thought that would happen is that the dengue models would be like useful in the beginning, and then it would kind of like stop being useful once the Zika models were just informed by like their own like number of like cases. And that was initially not what happened. And so initially we got that the models that were being informed by dengue were performing worse. So this is a plot on root mean squared error, which essentially like evaluates the accuracy of the point estimates of the model. And in this case, like the lower the number in the RMSE, the better these estimates like are are being compared to like the actual like compared to the actual number of cases. But we found that if we allowed for more variability, and if we allowed for more variability, then the Zika, like the Zika models that were informed by dengue were doing better. So these two on the top are the late week, these two are the midweek, and these are like the early weeks. And this specifically, we ended up picking a standard deviation of 4, yes. And so we can see here a little bit more clearly that the RMSE was lower for the models of Zika with dengue than it was for the models that had no priors. And if we move this to the actual like Puerto Rico map, then we can see that for example, that the number of cases that were predicted by the Zika models that were informed were usually like closer to the actual number of cases than just like the models with no informed prior. So we can see that even if it's like we can see that there's these, for example, like Ponce, and that Ponce is like a little bit like darker, and so is Bayamón compared to like the no priors models. And then when the no prior models overestimated, and they also were putting more cases on just on San Juan. And the key takeaway is that we can, like, incorporating information from dengue did allow us to have better predictions for Zika. However, the degree to which the priors were informative and improved the models was contingent on the amount of variability. So if the priors are very narrow, they essentially constrict the model, and they constrict the model, and then it doesn't allow it. They weren't allowing for the model to be more flexible and adapt to like the new incoming data of Zika. And both of these things that I just did, both for prediction and clustering, required a lot of of acquiring data and cleaning it and crying and downloading and packages, and then like using those packages, and so internet was a crucial part of like the whole process for both of them. And internet access currently is not homogeneous. It's not homogeneously like distributed. It is reported that low-income households are less likely to have access to broadband or like faster internet, and they're also more likely to just not have internet access at all. And this is something that does not occur just in the US. This is something that can be seen also like throughout the whole world. There are countries that most of the population does not have access to internet versus other countries that are in the 75 to like almost 100 like range. And this is in a way a limitation on data science like training, because of course two of the assumptions are that you need a computer, and the second one being that you need stable internet access to be able to get the data, install the software, and access all the learning materials if you're trying to become a data scientist. And what we thought of was that maybe if we can front load most of the tasks that require internet, then we can help like ameliorate or bridge the gap in individuals that don't necessarily have like access to internet access like continuously. And data science as a tool is going to keep being relevant you can see here that that there was an estimate of that by 2020 we would be generating around like 35 like zettabytes of data, and we actually ended up generating closer to like 60. And it's estimated that by 2025 it's going to be like 175 like zettabytes. And this is just to say that data science is going, we're generating so much data, and getting information or actionable like information from that data is going to keep requiring like data scientists, and that this is a tool that is going to keep being like needed. And and then so we created a package that is part of the Carpentries Offline currently, and it essentially attempts to manage most of the content that would need to be downloaded and updated. So then, like, we have two use cases. We have a person that is going. We have, for example, like an instructor that is trying to go to give a talk, their own talk in this country that is in this country that has, or this area that has limited access to internet. So then they can take their own computer or a mini computer, such as like a Raspberry Pi, and then they can use it as a local server to then allow their students to download things directly from their computer. And the other use cases is this individual that is expecting to have limited access to internet, that they say like, okay, well, I'm gonna go to this field. It's not a field station, it's a field a field site. And then you have this person going to a field site that is expecting to not have internet, and maybe and then they can say like, okay, well, I want to learn this week about for loops, for example. And then they can use offline DataSci with essentially like two commands to quickly be able, with very little management, to like acquire a lot of the basic tools that are needed. And some of the key features are, for example, like are that we include are R and Python, which are open source statistical and graphing software, and IDEs, which are like integrated development environments that allow you to interact better with these languages. And we also mirror packages of repositories, and we also include their dependencies. And I think that most importantly is the online lesson material, because you essentially obtain an already rendered version of the pages that you want to be like going through or studying from. And then you have most of the same functionality that you would if you had internet. So you click on a link and you want to go to that next like lesson to that next lesson or module, and you can do it even if you're offline. And as I mentioned, you can do this like very easily. You can essentially use first just pip install, and you install like offline DataSci, and then you can just use offline DataSci install all, and provide it a path to where you want to save things, and things will be saved to your computer. And it's not just for your operating system. It can also, most of these things that we include here are for multiple operating systems. So you get R for Mac, and also for Windows. And so it's a way for you to be able to give like this workshop and say like, okay, well, I don't know what the students have. I can't assume that they all have like a Mac computer, and then so I can take with me like all of the things that they might be needing. And they also like they also kept like, they stay updated. So once you download, it checks to see like the last version, and then it'll download the last version if yours is already behind. And I'm very happy that we got to be part of the Carpentries Offline, because I think the Carpentries generally they are trying to bridge the gap, and they do wonderful work on data science instruction. And I'm I'm very grateful that I've gotten to collaborate with people, with the other teams like in the UK that we're working with for more of the server part of things. And yeah, so I really thank all of you for being here, and I have to I have to I have to say that I'm very thankful for my two wonderful advisors that have been my cheerleaders throughout like my whole experience, and I don't think I could have asked for better advisors, and they because they're I've learned on all sides of everything. I've learned to be a better person. I've learned to be kinder when I'm trying to give feedback to people. And so I've learned so many things from them that are not just academic, and they are definitely like my two role models. Um, and yeah, these are just some selected references. What do I do now? Oh, right, questions.
Okay, so thank you very much. That was wonderful. You did a really great job. So we actually are at time for the class. So if people need to sign off on Zoom or take off, that's totally fine. But if you're okay staying a couple extra minutes, maybe if anybody has any questions, we could do it like that.
Yeah.
Okay, awesome. Thank you so much.
Oh no, Orlando.
Hola, Virna.
Hola.
Felicidades, está súper
Thanks.
chévere. All right. It was fascinating, like from the perspective of history, how we are impacted by vector-borne disease, and then you ended with this part that might be revolutionize the way we teach in different places. I have a question actually in that part. So you mentioned that this code like is the pip install. Is that already? So if I want to teach a course in R in the middle of the Amazon in Colombia, can I do it right now? Or how is the process? When is going to be released?
Yeah, so currently there's already it is already released. I'm still looking forward to adding some more functionality to it as soon as I get to stop working on my dissertation. But yes, like currently it is something that it is a package that is already you can just install with pip install currently. And the caveat is that the lessons need to be online. Like but that the lessons currently as they are because we use wget to like download them and to crawl. So the lessons need to be online, such as like in the carpentries offline, but in such as in the carpentries, it's definitely like one of the things that I want to do most is that to allow people just to be able to include like their own to be able to include their own teaching material. But it's not to say, this is from like a website perspective of allowing people to click. It's not to say that, for example, you couldn't. That's like the server part of offline data site. But it's not to say that you couldn't just upload your slides and allow people to download them. So you could do that. It's just that if we're talking about like having all of the functionality of all of the pages in rendered in HTML, then they would need to be a website. But you could just include them like your what you're wanting to share with people. So yeah.
So much again.
Thanks all of you. Well, do I click on stop sharing? Oh, Sadie's here. Oh, thanks, Sadie.
Hola. Ciao.
Thanks for making it. This is great.